So last time we defined two things. We defined something called impulse and another thing called momentum. And we said that momentum is conserved. So I want to talk today about what we mean by conservation of momentum. Well, I think the best way to do that, again, per usual, is with an example. And I want to use the example of an inelastic collision. What do I mean by an inelastic collision? Basically what I mean is a collision where two objects end up sticking together. So let's suppose for the moment suppose you have a cart. And the cart is completely stationary. And the cart has a mass of, let's say, 20 kilograms. And you have some cheese. Here's some cheese. You know, all cheese wedges happen to look like Pac-Man. Actually, I'm realizing here I'm going to have two MCs. We'll say you have a wagon instead of a cart. But you do have some cheese here, and you have, this is like you go to the cheese shop and you get like one of those big wheels that you could roll down the street. So this is going to be a fairly heavy block of cheese. It's going to be a 10 kilogram block. It's like one of those big wedges of cheese that a mouse could live in. I watched too much Tom and Jerry growing up. And we're going to throw that big mass of cheese, we're going to throw that into the cart with some velocity, which I'm going to call VCI, for the initial velocity of cheese. Well, this is kind of the before picture for our collision. The after picture is going to look like this. You have a wagon, and you have some like mush of crumpled up cheese stuck to the wagon. But now the wagon is going to be moving forward. The wagon's going to have gained some velocity, which I will call v final. Now, my claim is that momentum is conserved, so that if I add up all of the momentum in the picture, the initial picture, you've got to get the same momentum in the final picture. So what that means is that if I add up all of the momentum from the initial picture, you've got to get the same momentum in the final picture. Let's see what that would mean for the final velocity of the wagon. Well, initially, the wagon has no momentum because it has no velocity, and momentum is the mass times the velocity. The only thing that has momentum is the cheese. So the cheese is going to have an initial momentum, the mass of the cheese, times the initial velocity of the cheese. So mc times v sub ci. That's my total initial momentum. What about my final momentum? Well, in the final picture, I've got one big chunk of mass, where it's the total of the wagon's mass and the cheese's mass. So that'll be mass of the wagon plus the mass of the cheese. And they're all moving together because they're stuck together. The cheese is smooshed right up against it. And it's going to be moving with some velocity v final. Well, using the conservation of momentum, using the fact that my total initial momentum has to equal my total final momentum, it's got to be true that, it's going to be true that mc VCI has to equal the total mass times Vf. So I can solve for the final velocity of the wagon and figure out how fast it's going to be going. So let's do that now. All we have to do to solve for Vf is move these two masses over to the other side. So we can say, let's see, I got to give myself a little bit of room here. Erase this and then go from there. So that would mean the 10 kilogram cheese times its initial velocity, which I didn't actually give you. Initial velocity was 3 meters per second. So we'll say that's 3 meters per second. Has to equal the total mass, which in this case will be the 10 kilograms of cheese plus the 20 kilograms of the wagon times the final. So in total we have 30 kilograms. And if I move that over to the other side, I'd be dividing by 30 kilograms. So we'll just take this guy, move it over to the other side. Doing out my math, you should see that V final is going to equal 1 meter per second. All I've done is said that the momentum, which is very easy to compute, the total momentum, in the before picture has to equal the total momentum in the after picture, and I can compute what the velocity has to be from that. We've discussed inelastic collisions, where two objects collide and they stick together. There's also what is known as elastic collisions, and they are another important case. This is when two objects bounce off of each other. And there's no mechanical deformations and no loss to heat where energy is going to be sapped away. If we're dealing with an elastic collision, it's going to be true that not only is momentum conserved, but energy, kinetic energy, is also going to be conserved as well. Now, in an inelastic collision, energy is conserved too, but some of it goes into deforming the material in other areas. So if you're just looking at the kinetic energy, it would seem that energy is not conserved. In an elastic collision, energy is definitely conserved. You can measure the change in the energy from before to after, and you find that there is no change in the energy. So we want to consider elastic collisions now, because it turns out they're a bit harder to solve than inelastic collisions, because we also have to consider that kinetic energy is going to be conserved. So in this picture, I've got a superball of mass A, MA, is going to be 2 kilograms, so a fairly big superball. And it's traveling with an initial velocity of 3 meters per second, and it's going to hit our wagon. I've changed up my notation a little bit, just to have fairly easy notation. I'm going to call the wagon B, so it's going to get a mass MB. Wagon still has a mass of 20 kilograms. But now, since it's a superball and not a lump of cheese, the superball is going to bounce back. It's going to bounce back. The wagon is going to move forward a little bit. So the superball comes in, bounces off this way, the wagon goes that way, the superball and the wagon are moving away from each other. That's what an elastic collision is going to look like. It's going to be things bouncing off of each other. So I want to come up with some equations that describe this system, because I want to predict how fast the superball and the wagon are going to be moving away from each other at the end. To do that, it's fairly straightforward to set up the equations. All I have to do is say that my initial momentum, total momentum, so I sum up all the momentums, has to be the same as my final total momentum. And it's fairly easy to write an equation for that. All we do is we say the mass A times its initial velocity plus mass B times its initial velocity has to equal mass A times its final velocity plus mass B times its final velocity. Similarly, it must be true that kinetic energy is conserved, which means the sum of the total kinetic energy initially has to equal the sum of the total kinetic energy in the final picture. That will mean that 1/2 mass A times its initial velocity squared plus 1/2 mass B times its initial velocity squared has to equal 1/2 mass A times its final velocity squared plus 1/2 mass B times its final velocity squared. Fairly easy to set that up. All I did is I looked at all the possible momentums in the beginning, looked at all the possible momentums at the end, did the same thing with kinetic energy, added them all up, set them equal to each other. Well, now we've got to solve. So let's see how that's going to work. I'm going to plug numbers in to make this a little bit easier. Well, first, I know the wagon has no initial velocity, so I'm just going to set that equal to 0. That term goes away. Same thing on this side. Term goes away. Then we have mass A times its initial velocity. So that's going to be 2 kilograms times 3 meters per second. Easy enough to do. Has to equal, again, 2 kilograms times the final velocity of A plus 20 kilograms times the final velocity of B. This should be the final velocity for B. I can do the same thing with the kinetic energy. Let's see, that's going to be 1/2 the mass, so 1/2 of mass A is going to be 1 kilogram times the initial velocity squared, so that's going to be 3 meters per second squared, 3.0 really, has to equal, I'm running out of room here, so I'm just going to give myself a bit more room. Try that one more time. So that'll be 1/2 the mass of A, which was 2 kilograms, times the velocity of A, which is 3 meters per second, whole thing squared. And that's got to equal, let's see, 1/2 the mass of A, which is again 2 kilograms, times, let's see, its final velocity squared, plus 1/2 20 kilograms, times B's final velocity squared, running out of room there still. Now that I have numbers in here, I can simplify this equation quite a bit. 2 times 3 is 6. And in fact, I'm going to cancel a few things. I'm going to just cancel all my kilograms here to make this easier to write. So this is going to be 6 meters per second equals 2 VA final plus 20 VB final so it's an equation for the final velocity of A and B. But I need 2 equations to solve for this since I have 2 variables. So that's where the kinetic energy equation comes in. So let's see, this will be 1/2 of 2, which is going to give me 1 kilogram. Again, I'm going to cancel my kilograms here. 1/2 of 2 again gives me 1 kilogram. 1/2 of 20 gives me 10 kilograms. So we are going to be left with, let's see, this is going to be 9 meters per second, meters squared per second squared because it's squared, equals VAF squared plus 10 VBF squared. So I've got 2 equations. I've got an equation for the final velocity of the superball, VAF, and I've got another equation for the final velocity of the wagon, VBF. The problem is that these equations turn out to be difficult to solve. You'll end up with a quadratic equation, and those tend to be a bit nasty and involve lots of algebra. Totally doable, but not very fun. So as we've as we've discussed before, there are easier ways to solve these equations. If you go online, there's any number of equation solvers. If you have access to Mathematica, that's my personal preference. Wolfram will probably, Wolfram Alpha might be able to do this for you as well. But let's see now how we can solve, how we can enter this equation into Mathematica to solve these equations, rather than having to plug through on our own and solve a nasty quadratic equation. All right, let's solve the elastic collision problem using Mathematica rather than doing it out by hand, which would be more time-consuming and a bit more painful algebraically. So we want to start by opening Mathematica and pulling up a new Mathematica notebook. I've already done that. If you need to do it yourself, you can just go to File, New, Notebook, and that should pull up a new notebook window for you. So the first thing we want to do is enter the two equations we want to solve. And these two equations were for the conservation of energy and the conservation of momentum. Since it's a little bit easier, I'm going to start with the conservation of momentum equation, which was just given by the mass A times A's initial velocity plus mass B times B's initial velocity. And we just set that equal to the mass A times its final velocity plus mass B times its final velocity. So the sums of the total momentum initially equals the total momentum in the final picture. One thing I'll note is you want to use the double equal sign here. That's not a mistake, but the double equal sign is what you use to test for equality, which is exactly what we want to do here. So just do double equal sign and hit a plus, or hit the space bar rather, and you should see it gets a little bit smaller. To make my life somewhat easy, I'm just going to copy and paste this over here and change all the initial velocities to final velocities. And that's my momentum equation. Okay. Next, what I want to do is write the same thing, but for the conservation of energy. So the kinetic energy has the formula 1/2. I am using the keyboard shortcuts to make the 1/2 sign. If you want, you can pull up the basic math input template, which gives you formulas for fractions and square roots and a whole bunch of other things. But I'm just going to enter it in this way. 1/2 mass A times the initial velocity of A squared plus mass B, 1/2 of mass B times the initial velocity of B squared. And just as I did before, we want the double equal sign. And I'm going to make my life easy by copying and pasting and just changing these to the final velocities. So we have these two equations that we want to solve. We've got our momentum equation and our conservation of energy equation. Now, many of the Mathematica commands are easy to remember because they're exactly what you'd think to call them. I want to solve these two equations for VA and VF. So all I'm going to do is type solve with a capital S, and I'm going to put these in curly brackets. Let me put a comma here. The curly brackets allow you to make a list. They're highlighted in green right now. They allow you to make a list. Now we're making a list of those two equations. And I need to tell Mathematica what I want to solve for. And what I want to solve for is the final velocity for the superball. So that's the final velocity of A, and the final velocity of B, which was the wagon. Once I've set my equations up like this, I can run the evaluation by hitting Shift-Enter. And you can see you can figure out what these are. We have, in fact, there are two solutions. If I look here, we see that the final A velocity is the same as the initial velocity. The final B velocity is the same as the initial velocity. Well, it turns out that one easy way of conserving momentum is just to keep it the same momentums that you started with. So this is not the solution we want. The solution we actually want is over here, which is a bit more complicated. So we could plug into these formulas. You could write these down and then keep it in variables, or you could write it down and then try to plug in later. But it's easiest just to put in the parameters we had before. So we know that the mass of A, I had given you, was 2 kilograms. So I'm going to write mass A is 2 kilograms. I do not want to put the kilograms in here because Mathematica, there is a way to work with units, but it's a bit complicated. So we're going to skip the units for now. We'll just assume that we're just working in kilograms. Mass B, we said, was 20 kilograms, so I'll just write mass B is 20. You'll notice that I'm putting a semicolon at the end here. The semicolon is just there so that I don't end up printing that line out. It doesn't really do too much. You can leave it off if you really want to, but it makes the output nicer, so it's better to have there. Let's see, I need to specify my initial A velocity, which we said was 3 meters per second. And I need to specify my initial V velocity, which we said was 0. And if I evaluate now, I should get down here, instead of the equations for A and B, it should give me the actual numbers because it will plug in the starting values that I gave you. And you can see it gives you a little bit of a warning message here telling you that it couldn't solve for exact coefficients. Don't worry about that. We're not going to pay too much attention to it. But what we will find is that if we, when we plug in, we will get the solutions for A and B. We'll get that the final A velocity is about negative 2.5, and the final B velocity is about 0.54. Continuing our discussion on angular quantities, we want to talk about one more angular version of a linear quantity, and that's going to be the angular momentum. So we know that there's this linear thing called momentum, which is equal to P, which is equal to the mass times the velocity, and that momentum is conserved. Well, it turns out there is another quantity called the angular momentum, which we represent by the letter L. And it too is also going to be conserved. Now, what is the angular momentum going to be equal to? Well, we've done a pretty good job of relating linear quantities to angular quantities just by mapping over the different versions. So, for example, velocity would become angular velocity, acceleration would become angular acceleration. Well, we know the angular equivalent of velocity is just the angular velocity. And we know the angular equivalent of mass is moment of inertia. So I'll just write down, it's going to be moment of inertia times angular velocity. So this is going to be our angular momentum. Couple of notes to make. Again, that's your moment of inertia. Which for a rigid object should be mostly constant. It's going to be constant for different rigid objects. And again, omega is just your angular velocity. As I mentioned, angular momentum is actually conserved. And there's a very nice demonstration of that. I'm going to let my student, Zach Lindeberg, show you that right now.
Change directions for him, too. They need to do it a little bit. All right.
Zach started to go faster and faster as he brought his arms in. Well, initially, he was in a situation like this with his arms spread out, holding some weights, and he has a certain moment of inertia when he's doing that. Remember that the moment of inertia depends not just on the mass, but how the mass is distributed about the axis of rotation. So we're rotating about this axis, Zach's rotating about that axis, and he's going to get a certain moment of inertia rotating about that axis. When I switch over to this picture, Zach pulls his arms in. His moment of inertia is now going to be smaller. It's going to be easier to rotate because, again, the mass is going to be distributed closer to the axis of rotation, which means it's going to be easier to rotate that mass. We can do a quick calculation of this. So suppose I'm looking at his initial angular momentum in the same way that we would look at initial momentum if we were conserving momentum. Well, Zach's angular momentum, I'm making up numbers here. Let's say it's 3 kilograms meters squared for that moment of inertia. And let's say he's going around at 1 revolution per second. For his angular velocity. Recall, angular momentum is equal to the moment of inertia times the angular velocity. Well, he's got to have the same final angular momentum, which means he's got to have an angular momentum of 3 kilograms meters squared revolutions per second. But if his moment of inertia changes, let's say his moment of inertia, because he's brought his arms in, remember his mass hasn't changed, but the distribution of mass has, which means the moment of inertia is going to change. It's going to get smaller. Let's say it goes down to 1 kilogram meters squared times some final angular velocity. My angular velocities, or Zach's angular velocity, has to go up to compensate. Because it's still going to be equal to that 3 kilograms meters squared revolutions per second. That being the case, if we solve for this, we would find that the final angular velocity, since the moment of inertia went down by a factor of 3, angular velocity has to go up by a factor of 3, so it would be 3 revolutions per second. So just like momentum is conserved, angular momentum is also conserved. This is why. This is also the reason why when you see figure skaters and they're doing that little thing where their legs out and they're spinning around really fast, when they pull their body in and start spinning around like that, they start going a lot faster. They're reducing their moment of inertia, which means their angular velocity has to increase because angular momentum is conserved.